Oh no! Kirby got stuck in a weed whacker. We have to get him out. Here's the Dissection rescue team who's gonna save Kirby. To find him, we need to know how a weed whacker works. A weed whacker is a gas-driven power tool used to trim grass and cut weeds in places that are difficult for a lawnmower to reach. The weed whacker's main components are a carburetor, two-stroke engine, flywheel, and clutch. Here's how it works. The air starts by flowing into an air intake port and through a filter. Then, it flows through the choke valve of the carburetor, where it mixes proportionally with fuel. Next, the mixture exits the carburetor through the throttle and enters the engine, where the spark plug ignites it. This spins the flywheel, which spins a shaft connected to the blades of the weed whacker. The weed whacker functions on a two-stroke engine, meaning that it completes a full power cycle in two steps, the upstroke and downstroke of the piston. When the air-fuel mixture enters the engine, a spark plug ignites it, causing combustion. The expansion of the mixture moves a piston, which converts to rotational power through a crankshaft that spins the flywheel. When the piston moves down, a vacuum is created, which draws in more air-fuel mixture.
The flywheel has many purposes. First, when using the pull starter, magnets on the flywheel spin past the coil, creating electrical current that fires the spark plug, which ignites the fuel in the cylinder. Second, its inertia ensures that the crankshaft keeps rotating even when no power is applied, preventing the engine from stalling. Third, it has airfoil that act as a fan, moving air across the engine to help dissipate heat and prevent overheating. Attached to the flywheel is a clutch, two semicircular metal pieces with a spring connected across their combined diameter. The clutch does not engage the shaft until it reaches a specific angular velocity, allowing the engine to spin up without external loads. Our main fluid component is the carburetor. Its purpose is to proportionally mix air and fuel for combustion in the piston. The carburetor has two valves, the choke controlling the amount of air entering the carburetor, and the throttle controlling the amount of air-fuel mixture that enters the piston. Between the two valves is the venturi, a variable cross-section pipe that mixes fuel and air. By narrowing the cross-section, the venturi speeds up the fluid and creates a low-pressure zone in the throat that drives fuel up from the fuel reservoir. We'll analyze this further with computation.
To maintain a steady fuel intake into the venturi, the fuel reservoir's opening is controlled by a needle valve actuated by a diaphragm. The diaphragm pushes on a lever based on the pressure drop within the reservoir, which is related to the speed of the exiting fuel. The needle valve allows the carburetor to function regardless of orientation, which is essential for the use of a weed whacker. For our analysis, we will solve for the speed at the throat, pressure drop in the venturi, and the viscous losses of the fuel inlet. We assume the air and fuel are in the ideal 14.7 to 1 ratio. Here is a diagram of our carburetor showing its geometry and dimensions, which we use in our analysis. First, we estimate the velocity of the air-fuel mixture as it exits the carburetor using our measurements and the rated angular velocity of the weed whacker. For every piston cycle, the engine displaces a volume of air. At the same time, the same amount of air must exit the carburetor. By multiplying the displaced volume by the engine speed, we obtain the volumetric flow rate of air from the carburetor. Dividing by the area of the carburetor exit, we find that the exit velocity of the air-fuel mixture is 21.3 meters per second.
We would also like to find the Mach number of the fluid going through the carburetor. By dividing the speed of the mixture by the speed of sound, we find that the Mach number is 0.06. This is well below 0.3, which allows us to assume the flow is incompressible. To calculate the speed of the air-fuel mixture at the throat, we use a 1D incompressible conservation of mass analysis. For this carburetor, we estimate the fluid speed at the throat is 40.4 meters per second. Next, we calculate the density of the fuel-air mixture using a weighted average of their respective densities. With this information, we can now use the Bernoulli equation to calculate the pressure drop at the throat. Picking a streamline that goes from far ahead of the inlet to the throat, we can cancel out the dynamic pressure term on the left because the fluid is stationary, far away from the carb. We can also cancel out the hydrostatic pressure term since the height of the air-fuel mixture stays roughly the same along the streamline. Altogether, we find the pressure drop across the carburetor is approximately 1,000 pascals. Now that sucks.
For an extra sanity check, we can calculate the Reynolds number at the exit. Since the flow is an air-fuel mixture, we approximate its properties by using a weighted average for the viscosity. Plugging in our measurements of the fluid speed and exit diameter, we find that the Reynolds number is around 250,000, well into the turbulent regime. So far, all of the analysis we've done assumes that there are no viscous losses, but to be sure, let's go through with the calculation. We'll specifically look at the losses across the fuel intake pipe. First, the exit speed of fuel is calculated by assuming that the fuel-to-air ratio is 14.7. From there, we calculate the Reynolds number, and using both of those results, we calculate the friction factor. Pulling all of that information together, we calculate delta B, which we find to be around 10 pascals. Overall, this loss due to viscous force is not significant, but if the pipe had a small diameter or was longer, these losses would be higher. Through our analysis of the weed whacker, we discovered that the true Kirby was within us all along.